right, lecture number 3. Welcome to the course. This is a purely recorded lecture for the first time of my life, so I'm not quite sure how well this works. But let me get started. So, this course is about introduction to robotics, and robotics has a whole number of foundations. And one of the foundations, which is really important in robotics, is linear control. So linear control is really something which we understand much better than nonlinear control. It's about linear systems. Linear systems is usually about linear algebra, and we know how to manipulate linear algebra. Now, I really don't want to go too much into linear systems, and there's complete textbooks on this topic. But I do want that you know the foundations of linear control, since the foundations of linear control are always part of any nonlinear control. So what we're going to do today is essentially we go through the basics concepts of linear control theory. If you want to get more depth on linear control theory, you can go to any library or any online store these days. There are literally hundreds of books on linear control theory. You can choose the one that you like the best in terms of notation, in terms of writing style, or whatever you want to get some more in-depth information. We will cover, and this is generically in this course, we will cover just that, what is important for us in this course. We do not cover all and everything. Very important. So what am I after today? So we need to talk about the basic concepts of linear control theory, like the plant model, continuous versus discrete systems, the control policy, desired trajectories, open loop control, feedback control. These are things actually I mentioned in the intro lecture already a little bit, but they will come another time. We'll talk more in detail about PD control and PID control, negative feedback control, linear systems, block diagrams, and we do a little bit of an example just to give you a feeling what's going on. So this is a fair amount of topics. None of them is particularly complicated, you will see. And all of this should in theory build on mathematical knowledge, linear algebra knowledge, a little bit of differential calculus, which you have seen before. So let's see how this works. Okay, so the robot, plant, or whatever you want to call it. Plant comes from the old word of industry, where basically the control system was maybe an entire factory line, and so people used this word for a long time. It's still being used in some robotics books. Most of the time, we will call it a robot. And there's two major systems. There's continuous systems, and there's discrete systems. So let's just develop this for a moment. So we have here essentially the robot dynamics. Okay, and what does the robot dynamics get? It basically gets an input U, and then it responds to that with a change of state, which we usually call x dot. So x dot is where x is the state, and x dot is the change of state. So in order to then figure out where the robot will be in the future, you need to integrate this kind of change of state variable, and that is usually done here with an integrator. And then this finally gives you the position x. Now, essentially the robot itself does all of this for you. So you can draw a box around this like this, and it simply integrates after getting a command U, the change of state, and what you can observe is the robot in state X. So that entire box with all the stuff inside is what we normally call the robot plant. Then we have the inputs or commands, and the outputs or the state of the robot. That is the state which describes the entire robot. We'll talk more about this, what it actually means to describe an entire robot. What level of detail do you need? But for right now, we're doing fine. Now, in discrete systems, continuous systems means we're doing continuous time. Discrete systems, we do time steps, delta t, which is much more natural of what's going to happen on a digital computer when you implement it, since you usually have to run things out of a clock. The digital computer, in the end, is not a continuous machine, although it can approximate at some point pretty much continuous differential equations if you just do discretize the time step small enough. In robotics, we usually run control systems between 100 Hertz and 5 kilohertz. These are significant time steps, and discrete systems actually matter. And you will actually see in one of the next lectures how the change from a continuous system to a discrete system makes actually a big difference in how stable a system can be. Now let's look at the discrete system. The discrete system now here, so this here was the continuous system. Continuous system, the discrete system, similar box as before. But now we get a command U. Now look at the superscript n, a time un. And this is given to the robot dynamics. And out comes directly a time, a state at the next time step, xn plus 1. Okay, yes. And yes, importantly, I should mention, I forgot this before, we always have feedback, of course, of the state back to the robot box, of the state back to the robot box. Since the robot dynamics obviously has inherent knowledge where it is as a physical system, so the state is just inherent in the system. So discrete systems omit the dot variable by directly going from where I am currently to where I am at delta t in the future. So there's always inherently some kind of a delta t time step. Very important. And if you change the delta t, make it very big, the dynamics of the change system change, and also the stability properties make it very small. They will be in a particular way as well. Okay. So this is the intuition. So we call these entire boxes, and we will never go into the details what's inside the boxes. We call those the robot or the plant, and we don't care about anything else that a U comes in and a state comes out. U comes in, state comes out. What's happening inside is what the physics do and how it's being sent by our system, but that's essentially it. One more point. It is always possible to transform a continuous time system into a discrete time system. And we come back to this since we have to do this a couple of times. It is not always possible to transform a discrete time system into a continuous time system. Certain systems inherently are discrete and cannot make a continuous system. So this is just a little bit background information. Good. Now that we have this, the next step we have to do is we have to put this into equations. Not very complicated. So the continuous time system is always characterized by x dot equals some function of the state x, the command u, and some time parameters t. Notice, please, on the slides, these are boldface x's, boldface u's. That means all of these things are vector equations. This is a vector value function. I could all write this like this. The same thing here for the discrete system. I can basically write x n plus 1 equals f of xn, the current state, plus un, oh, sorry, not plus, obviously, comma, un, and now we don't use time, we use n for the discrete time step number n. Okay. So this models the dynamics, totally general. And it's good in general robotics, you want to start with a very general picture, describe things in general, and then start focusing step by step in. So depending on what system you're working with, you want to focus in and basically look at the realization of these equations for a particular control system. But it's great if you can derive things in grand general first, and only at the very latest step kind of make things more concrete. Cool. Some notation which is important. Well, I should first, well, let me add this. In terms of observations, so the system dynamics models how the system changes over time. And there is an output equation or observation equation, as people call it in control. That models how you can actually measure things. What can you observe? And it's a similar equation. It's now called G. It depends on the state, the command, and the time. And it just tells you what you can observe. Like, for instance, in a robot system which has position encoders in every degree of freedom, you can only measure positions. You cannot measure velocities directly. So your y would just be a vector of positions, but not velocities. And there's many other examples where you basically cannot measure many other states of a robot. And these equations, you will see this later, we will need them at some point to basically estimate all the states which we need for control. What we observe is often not enough for control. So for instance, in many controllers, we need velocities. So we have to get some kind of estimation going how to get velocities. Just a simple example, how do you get velocities? It's very simple. So you do xn plus 1 minus xn over delta t. So that would be x dot, particularly if you make it xt really small. And it's a good approximation. So it's very easy from just 2 time steps to by numerical differentiation to get velocities. There's other states which are much, much harder to estimate. Like for instance, if you have a humanoid robot and you want to know the orientation of what is called the base coordinate system, let's call it the butt in this case, if it's a human system, it means where is the base coordinate system in space, in a 3D world, and what orientation does it have? Now, you don't have any sensor which gives you that. And estimating that information turns out to be quite tricky. You need gyroscopic sensors like IMUs, inertial measurement units, as they're called, and that's actually becoming very quickly a research topic. The same observation equation exists in discrete time systems, just depending now on the discrete variables. Nothing particularly changed. Some useful notation which we want to emphasize. So if it's about this t in here, if a system like this has a direct time dependency, we call it a time variant or non-stationary or non-autonomous. Now these are basically words which were coined in different communities. Time variant usually comes from the control community. Non-stationary comes off more from the estimation or machine learning community. Non-autonomous comes from the complex systems or dynamic systems perspective. All means the same. What is a time-dependent system? Most systems are not time-dependent. But there's some, and they're very profound, which depend on time, like a rocket. You take a rocket, you shoot it up in the sky. While it's shooting up, it's losing mass since it's pushing out gases. And while its mass changes, the control dynamics change. So here you have a typical system where time, which is time dependent, where basically the system changes over time. Now, most of us, a normal robot or also your normal human being at a particular age, if you don't look over many years, they're pretty stationary. They don't change so much. Okay, you can eat a lot, and your tummy gets really full, and then maybe you change a little bit because you can hardly move anymore, and then you become a time-dependent system. Most of the time, we will only look at actually time-invariant systems, or stationary or autonomous systems. This is really the domain which we care about. The other ones are special cases. They require more math and more work, but it's all doable again. All right, continuous systems, discrete systems, system dynamics, output equations or observation equations, or you could even call it entirely perception if you wanted to. If you want to go to the level of visual processing and other sensory processes. And we have time variant and time invariant systems. It's just notation. You will hear it all the time in robotics, in many conferences and many things. Good. So let's do an example system. And often I show you a slide, just don't get confused. I show you a slide, but I develop it on the whiteboard again just to make things clear how it becomes being. This way, also, I'm not just flashing through slides and give you a moment to look at things and digest things. All right, so here we go. We want to model a pendulum system. And it's a very simple system. It has here simply an electric motor, for instance. Then there is a rod. At the end of the rod, we assume we have a little point mass, which has mass n. And I just make it a point mass to keep things simple at this moment. Then what else do we need? We basically have to say how long is this rod. It has length L. We need something which describes the pendulum position. So it can only swing here around like this. And we call the position variable here Q. You can also, many people in robotics also like theta. Actually here my slides seem to have moved and make the Q a theta. So let's make it a theta for the moment, since the equations will use theta in the end. We have to define how the pendulum is positioned in the world. That basically means where is gravity? If gravity is pointing down, remember gravity is that magic number of 9.81 meter per second square. In case you forgot about this. What else do we need? We have this motor, and it creates a torque, and the torque we call tau. Okay, so this kind of, with a nice little sketch, describes what we want to do. Now, how do we get the equations of motion, which are basically shown here already? So the development of that is usually, and we go back to this actually in a couple of lectures, how to do this in a more formal way. Right now, we just do it in an intuitive way. And one of the important insights of basic physics is that all forces have to be balanced, and all torques have to be balanced. In this particular case, we do everything in the torque world because this is a motor, and it can only create a torque and not a linear force. There's other motors which can create linear forces. They're like pistons, but that's not what we're going to do right now. So let's see, what do we need? All forces, all torques have to be balanced. One important torque is the inertial torque. So this is here, I theta double dot. This is the inertia. This is the acceleration of the pendulum. We'll get back to inertia in a moment. Not in a moment, in a couple of lectures from now, how they're officially defined and how they're actually even derived. You will see it comes automatically out of some physics equation. Right now, the inertia is simply basically the resistance a body with mass in kind of volume has when you try to push it or to rotate it. Good. So this is what is called the inertial torque. The inertial torque needs to be balanced by all external torques. A very simple external torque is obviously, I have to equal this, is the torque which I'm applying here from the outside. By the way, we need some convention, what we call positive and negative when it comes to torques. And there is what is called the right hand rule. Very simple. You take your thumb, you stick it in the direction of your positive rotation axis, and then you say with your fingers curl in the direction of a positive torque. So if you look at this, and we basically have a arrow in this direction, so actually our thumb has to stick into the whiteboard, and we basically have to curl in this direction, and that is going to be our positive torque. So we define this here actually as positive, importantly. And that's just a matter of definition. It is something you can just redefine in the other direction. You just have to be consistent. So we call this a positive torque generated by the motor. And now we have to see what other torques we have. And there's only one torque, and it comes basically from the gravity force. So let's look at this. So we have here a force, which is basically F due to gravity. Now, what is that force? It is essentially F gravity is the mass times a moment arm. So the moment arm here is essentially that distance from the motor. So what is that? This is basically the length of that pendulum times what? The sine of theta. Okay, this here, this is angle theta, sine of theta. Remember triangle gauge geometry, that gives you that. M times L times sine of theta, and we have to add times G. So that basically gives us all we need. And we have to agree on the sign. Now, so gravity right now is pointing down. So it's trying to push the pendulum back. So against what we defined as a positive torque. So we need to put a negative sign in front of it. Okay? So we can now complete these equations and basically write here minus MLG sine theta. All right, we have that. Cool, and that's exactly the same equation that's here. Just wanted to tell you where it comes from. Next thing, let's see whether we can simplify the inertia of a point mass. That's the reason why we made it a point mass, because it's so simple. The inertia of a point mass I is simply the mass times the distance squared relative to the rotation point. So here's a mass, it rotates about this point with distance L, so ML squared is the inertia of a point mass. Good, and so we can actually insert this here. Beauty about a whiteboard, I can erase stuff and just ML squared here. And now we have, in this equation, everything we wanted to express. And not simply we want to basically solve it, we want to make it a differential equation. That means the system dynamics, that means all the state change variables are on the left, the other ones are on the right. So let's bring this on the other side. So we get theta double dot equals tau over ML squared minus, now the M here cancels. Then we have 1L, which cancels as well. So we simply get G over L times sine theta. And these are our equations. Okay? That is hopefully exactly the same what is written here. Just checking. Fine. Question of the day. What is a double dot? Haven't we just talked about single dots all the time? Where's the double dot coming from? Now, it turns out that normal inertial systems are described by a state which is position and velocity. So everything which is a system with mass has at least a position and velocity. That describes the state. And the change of state is actually the derivative of velocity, that is acceleration. So that's why we basically have double dots here. You will see in a moment you can always transform a higher order differential equation, this is called a second order differential equation, into multiple first order differential equations. That means a vector of first order differential equations. This is always doable, and this is essentially the reason why we only work with this final notation x equals f of x u of t. We do not have to think about double dots. All this goes away. Despite sometimes it's useful to use the double dots because accelerations have a physical meaning to us. If we put everything into vector equations, we sometimes lose the physical meaning, and that's not always the right thing to do. Cool. So we derived, just in a very ad hoc, intuitive way, a model of a system. We haven't done any observation equations in this particular case. Observation equation would, for instance, just be that, can we write this down? If you can only observe here with a position sensor the position theta of the pendulum, well, then you could just write y equals the complete state of the system is obviously equals theta and theta dot. This is the complete state. Well, how do I just select theta out of that? It's very simple. I take a row vector which 1, 0, and this way I get y. So 1 times theta, 0 times theta dot is just theta. So y equals theta. That's one way of writing the observation equation in this particular case, and then you would have to numerically differentiate theta in order to get theta dot. Cool. So let me move on to the next slide. The next component we need is the control policy. And let me see. The control policy is now about what the computer computes to send to the robot to make the robot have a desired behavior. And in some sense, control policies is all what you need in life. If you know for every behavior you care about, and I mentioned that I think also in the intro lecture, if you know a control policy for playing tennis, for chopping vegetables, for walking, for scratching, for dancing, or whatever, then you can basically use this thing. It will basically, based on the desired behavior, which might be dancing, create that command U based on this feedback of the state in which the robot is, and outputs the right motor command. You will be doing the right thing, and everything will be perfect. So not a particular big deal. In some sense, actually, the last 15 years, the trend how artificial intelligence is being taught is actually to start thinking about artificial intelligence as a decision process. And robotics is essentially doing continuous decisions. So if you look at the textbook of Russell and Norvig, which is the kind of standard textbook in artificial intelligence, it actually starts to be based very much about control theory or reinforcement learning or decision making and planning and how to learn how to decision making. And essentially robotics can be thought as one particular fundamental part where you work with physics equation and continuous differential equations. So let me get rid of what's right here. May need this later on again. And so the control policy is, in general, simply written as pi equals, U equals pi as a function of state, some parameters alpha, and potentially time t. So this is the policy. Very, very general. Again, if you knew this function, things would be great. We'll talk about what the parameters mean. We'll talk about what time means. We'll get all back to this. In general, also, the desired behavior can be different things. So the desired behavior needs to be formalized at some point. And you could, for instance, say it's an external reward, like you can play this old game, you close your eyes, you walk around, the people around you say hot, hot, cold, cold, and you this way point to some particular target. So it's a very simple form of getting this very simple, discrete reward signal, whether you get closer or further away from your goal. You can make this more precise. You can actually provide people a complete optimization function. For instance, you could say here's an optimization function J, which says I penalize you if you are a certain amount away from a desired state, which could look like this. So desired state is where I want to be. This is where I am. I square this, which basically describes the distance. The factor 1/2 is just for fun. I shouldn't do this. The proper one should not be interpreted as a 7. And that basically now codes in an optimization function where your goal is. And you can even be more precise. If someone already did this for you, you can have a precise desired trajectory over time. It's like a spaghetti over time which you want to follow. And then basically you just say, I want to track this trajectory. So that's the technical word people use. It's tracking. I want to track this trajectory and follow it all the way. So different levels of specificity. The reward component is most likely the most general way of specifying what a policy is supposed to do, but it's also the hardest then to basically figure out the policy. The desired trajectory is the most specific thing what you're supposed to do, and it's then much easier to create a policy, how to work and realize that. Cool. Let's go to the next slide. Let's go, and I did this actually in the intro lecture, but let's do it again. Let's go and look into the different possible realizations of a control policy. One possibility is open loop control, what you see in the top here. So you have a desired behavior, a controller outputs a motor command, gives it to the robot, the state comes out, but there's no feedback. So what you see here in the policy equation, you simply erase the state variable. You do not depend on this thing anymore. This would be a new open loop if you wanted to. Give it a subindex. Now, where is this useful? We talked about this for a moment, but we just repeat. Most of the time, you always want to get state feedback. You don't want to run around blindly and hope you get somewhere. But if in your feedback loop, like shown here, if there's a strong delay, like for instance, in our human nervous system, the delays are quickly 30, 40, 50 milliseconds, or even 200, 300 milliseconds. It sounds very little, like that much. For control systems, it's terrible. And if you have delays, for instance, using feed-forward command in order to do a fast movement and only turn on feedback control when you are close and slower moving is often the right thing to do. So that's what we often do. Like here's a pen, I want to grasp it. My initial approach, my fast approach to the pen was most of the time open loop. But then when I start touching it and get feedback, then I go into a feedback scenario. Now, the closed loop control is obviously the full system, which just has the feedback loop complete, and we have the X back in the equation. Cool. Now, let's go one more time into the different types of feedback control. Here are 3 different diagrams: feedback control, negative feedback, and feed-forward control. I also mentioned that in the intro lecture, but it's an important concept, and let's look at it one more time. So feedback control is, again, just what we already had. It's the most generic way. We do not make any particular assumption about this control policy box. Now, negative feedback control is actually interesting. You see here at the beginning, there's something like there's a circle. In comes the desired state, X desired, and it gets also feedback from the current state, X. The desired state comes in with a positive sign. The current state comes in with a negative sign. It means you basically add them up, which means essentially you do X desired minus X. And that is a feedback error, a negative feedback signal. This signal is put into a feedback controller, which you will see in a second, and creates what is called a feedback command. So just going back to my equation here, so I now suddenly have here X desired. Now let me actually write this differently so we can make this clear. This here is an error E. I now depend on E, alpha, and T. So this is a different kind of state. The error is not the full state information. It just tells me the difference between my desired and where I want to be. Okay. So what this is good for is if you have a desired trajectory and you need to do error correction. And that is what's typically happened in a tracking controller. You want to follow a desired trajectory. This desired trajectory changes over time, and you want to basically stay close to it, and basically the feedback controller pushes it towards this desired trajectory. What is important is to, at some point, combine negative feedback control and feed-forward control. This is shown here. You have now the feedback controller, as you had before, and you have the feed-forward controller, which basically wraps around it. There's 2 signals from the feedback controller and the feed-forward controller added together and given to the robot. So the feed-forward controller is usually a nonlinear controller, and we will talk much more about this, since this is what all about nonlinear modeling is going to be in robotics. And it's very powerful to give you the right amount of push forward. The feedback controller is the error correcting controller. Remember, the feed-forward controller has no feedback. Here, the signal is directly coming from the desired state, going up here to the feed-forward controller, and then to the robot. It does not get feedback from the environment. So in this way, the feed-forward can only give you the right amount of pushing forward. The feedback controller does the error correction, which is really important. Error correction is, without error correction, you cannot be stable. Without someone telling you how much you're off from your target, you will not find home at some point. So if you close your eyes, you will just deviate more and more and more, and instead of going to downtown, it will turn up to be at the coast. All right, now we have this general picture. Now, these are typical block diagrams in robotics. Now, you will see them all the time. and we will now go over to making these more little bit equations. Here we go. So let me erase things here. And I want to basically go to formalize the different controller kinds in more detail, in particular the negative feedback control. So we had the generic equation. I should actually have not erased that. So we have U feedback equals some control policy of error, then potentially parameters alpha and time. Now there are several specific forms of this feedback control. The first one is called proportional control, which basically looks into position errors. So here, we just basically look into the error to be x desired if position minus x. And the way we instantiate this controller is as a linear controller. That means we actually simply write that this proportional control law is the error in position multiplied by a positive constant. This positive constant is called a gain or gain matrix. So let's look at this in more detail. So we have now U proportional equals some positive multiplier Kp times desired position minus current position. And obviously, all these variables depend on time. They change over time. And importantly, this is right now just referring to positions, not velocities. We'll see velocities in a second. These equations are written as vector equations. That means if this is a vector equation, then Kp cannot be a scalar multiplier. Well, it could be, but it's usually a gain matrix. Most of the time, this Kp would be a diagonal matrix, which we now know very nicely. That means there is Kp1, Kp2 on the diagonal, and zeros elsewhere. Off-diagonal terms are hard to understand and not very common. So what is this thing doing? Let's look at this idea for one moment. Oops, I erased too much. If you are a very simple system here, living on this axis x, and let's make this here your x desired. Okay? Now let's assume you're currently here at this point. It means if you're here, then x desired minus x, this point here, is going to be greater 0. If you're greater 0 and multiply this with a positive constant, then you create a force which pushes you towards the goal. Perfect. Now let's take this other point here. Let's assume you are here. That means currently you actually have overshot. You're too far away already. Let's write these equations for 1 second, like x desired minus O. Now this is going to be less than 0, negative. Means now, if you multiply this with a positive constant, you will be pushed backward. Okay, perfect. We get pushed towards the goal in 2 cases, and that's exactly what we want. That means in the end, we should end up at the goal. The next component, so this is proportional control, position error, which is the most important component to get you to a goal and to basically make sure you will stay there. The second component is derivative control, which is about damping. Now you basically write the same equations as you had before. Let me get rid of these things. You have now a dot here, and we call this KB. Again, a positive gain matrix, positive scalar multipliers, multiplying an error in velocity. This area is actually important when you start with, if you get pushed to the goal, you may start oscillating around it. And actually, if you want to be stationary at the goal, if you penalize for the movement, that means that you actually want to have zero desired velocity, then you will come to a stop. So that kind of damping is actually critically important to dampen the movement out of the system to come to a full stop. You will see how much damping matters actually in a couple of little examples which we're going to calculate. Okay, this is called derivative control because it's about the derivative of the position state, that means velocity. Last but not least comes integral control. Integral control is about saying that you create a motor command which is proportional to integrating up the error over time. So let's write this for a second as a big equation. Oopsie. So now we have x desired minus x as a function of time, of course. And we're going to integrate this over time. And this is like summing up errors over time in the end. An integral, if you do it discrete time, is just nothing but a sum. And then you multiply it with a gain matrix ki for integral, and this is going to be your integral command. So what is this useful for? So here is essentially the problem of P, proportional, and D, control. So let's assume you're a system who wants to push against gravity. Okay? So I want my arm here to be up here. But, so how am I going to do this? I only have a P and a D term. So I have only a proportional derivative control. So my desired velocity is 0 up here at a particular position. We'll calculate this in a second. Now, let's assume I reach that position. That means I'm exactly at my desired. So what kind of a control command is the PD controller going to generate? Well, I'm at the perfect position. That means my position error is 0. So the proportional command is not going to do anything. It's going to be 0. And I'm also standing still. It means I'm at the desired velocity, which is 0. It means my derivative equation is not going to do anything either. So I actually create 0 motor command at this position. But gravity is still pushing me down. Boom, I'm going to go down. So this controller, the PD controller, cannot hold out against gravity in a particular position which I want to achieve. But if you have an integral term, it means you're here, but you fall down. But now you have an error left. And this error now starts to get summed up. This basically, you take this error, add it to, multiply it with k, and then basically create a motor command. It will get you a little bit up, and you get up, up, up until you finally reach the goal. Again, we'll see this in an example in a moment. But these are the most important 3 linear control kinds, which we always have in pretty much every controller at some point. So it is P, I, D control. Very important. Proportional, integral, derivative control. Not every time you have all of them. Sometimes you have only P, sometimes you have only I maybe, sometimes you have only D, sometimes you have arbitrary combinations, but usually one of them is available. All right, so what I want to do now is essentially try to make this a little bit more transparent by running this example through our pendulum equation, which we just derived. Okay, I need space. So, the pendulum with PD control. Again, you get the entire slide. You can look at this. I'm trying to develop the slide on the whiteboard so that we can do this step by step. So first of all, we started out before by having already the equations of motion of the pendulum. So it was theta double dot equals minus G over L times sine theta plus tau over ml squared. Okay, so these are our model equations. As I mentioned to you before, working with second order equations is often not the most convenient. So let's transform that into a system of 2 first order equations. You will see it's very simple. We just do it right now intuitively. And in one of the future lectures, we do it more formally with what is called the Taylor series expansion, something you've seen before, but you might want to be reminded of that. So let's do variable substitution. We basically say x1 equals theta dot. So that corresponds to the velocity, the angular velocity of the pendulum, and x2 equals theta. All right. Now let's plug this substitution into these equations, into our model equation, and see what comes out of that. Now here from x1 equals theta dot, we get automatically, obviously, that x1 dot equals theta double dot. Okay. And do we need anything else? And this is, well, we get the other thing here, obviously, that x2 dot equals x1 equals theta dot. Okay. Now let's do substitution. So theta double dot here, it's substituting by x1 dot. x1 dot equals minus g over L. Nothing has changed, times sine of theta. Now we say theta is x2 plus tau over ml squared. So that is straightforward. And now we have one equation which is about x1 dot. The second equation we actually already wrote down here. So this is this guy. The second equation we get is x2 dot equals x1. And this is now our system of two first-order equations. And okay, so this should be written here. And we can basically do one step further, as shown here on the slide. We can basically write this now as a vector matrix equation. That's useful. So let me just punch that in here. It's kind of nice on a whiteboard. So I just make this a vector, which equals the matrix here, which has a term which depends on x2 and x1. And then it has this control term. And I will just basically write the control command separately. Tau is our control times some vector, which is 1 over ml squared. And the second equation didn't have any control term, so it gets a 0. So now we have a vector matrix equation of the system. Good. What comes next? We want a particular goal for our pendulum system. So the goal is going to be, we want to be that the position is at a particular desired state, xd, the velocity is 0. So remember, x1 is the velocity, x2 is the position. So we can write this here just for a moment. So x1 is supposed to be 0, the velocity, x2 is supposed to be x desired. And we want to create a PD controller to get us there. So this is shown here on the slide, and I just write it down one more time. So the PD controller for this would be that tau equals, also we can call it u, equals a position gain times the error in position. This is x desired minus x plus a derivative gain times x dot desired, the velocity desired is 0 minus x dot. And I forgot to write things here. This was x2, this here is x1. Okay, so this equation is shown here. And last but not least, what we're going to do now is we're going to insert that command into our model equations. So I'm going to clean up here to make this more readable. I'm basically trying to rewrite the equation down here, which says x1 dot and x2 dot equals our system, which is going to be currently minus g over L sine x2 and x1 at the bottom. Now our PD controller inserted plus kp times x desired minus x2 plus kb times 0 minus x1. And then I have to basically put this all in parentheses, so let me make some parentheses around this, and multiply it with 1 over ml squared 0. Okay, we just squished it there, should be all there. It's there. Okay, so this is just this equation, basically you have this equation inserting tau and putting the u in there. And now one interesting question to ask is, if I have a control system like this, with a control law, which I wrote like this, the PD controller, where will the system actually settle? Where will it end up? So that is what is called an equilibrium point analysis. So where is the system going to come to rest? And it's actually not very hard to do. So what we usually say is, well, when the system comes to rest, the change of state variables have to become 0. So if you go here, that essentially means we assume that x1 dot and x2 dot become 0. And then we see what that means. So let's try this and say this is 0 and this is 0. And let's analyze what that means. Now, all we're going to do is essentially we look at the first equation of this, and we look at the second equation of this and see what it means. Now, it's very easy to start with the second equation. So it has a 0 here, an x1 there, and then has a 0 multiplying this term, so this one goes away. So what we get as a first result is essentially x1 equals 0. So this is now the equilibrium point, point. Okay, x1 has to be 0, which is exactly what we want. So the velocity at the equilibrium point has to be 0. That's not surprising. It's the correct reason. You have to stand still. More interesting is obviously the upper part of the equation. Now let's write that thing out, but use our knowledge that x1 is 0 already. So we have essentially 0 equals minus g over L sine x2. That's one part. Now we have the PD controller, but we know that x1 is going to be 0. So we can actually drop that term. We just have the p term left over. So we have plus kp times x desired minus x2. And that has to be multiplied by 1 over ml squared. Okay, now that describes, hopefully correctly, let me double check what's here. That describes our equilibrium point for the position variable. Now all what we got to do is essentially we have to solve for x2. Here is x2 and where is x2? Now, how hard is that? Who knows how to solve that? And the answer is, none of you knows how to solve that. That's an equation which we cannot analytically solve, unfortunately. Sine x squared at x, so we cannot basically isolate x, not x squared, x2. Sine x2 at x2, we cannot, in these two different terms, we cannot isolate x2 on one side. It's just not working, so we have to find other solution methods. So let's look at that. So we still need to find the equilibrium point, so x2. What possibilities do we have? We have either graphical methods, or we have approximate methods, or we have numerical solution methods. So graphical is something useful to just remind yourself. I'll just give you a quick picture here. So let me see, what would I just put this here. The story is essentially here you have a term which is a sine term. Here you have a term which is actually a linear equation with a negative x2. So what this actually does in a real world, if you would just write x2 in this direction, then this first function term is something like a sine. Now, a sine should look like this. This term here is a term which is a negative slope linear thing, so which may, for instance, look like this. And we are interested where the two terms basically, where the one would have had maybe the negative sign. So always annoying. Fine, I can fix this. The negative sign looks like this. So we're now interested in where the two terms intersect. It means the one term is equal to the other term. Have I done this correctly now? Negative. No, I'm an idiot. Sorry, let me just do this one more time. Okay, restart. My initial plot was totally correct. So we have something like a sine wave. This is x2. We have a linear thing like this. We look at the intersection, and that is basically where g over L sine x2 would be equal to kp xt minus x2. And given that this is a negative sign, you would get 0, and that would be the appropriate x2, where you'll find your equilibrium point. So this is a graphical way of solving this. Not very accurate, but it gives you a good shot. There's obviously a complete numerical way. You just put this into a simple numerical root finder, and you get a solution. And MATLAB can do this, and many other programs. I want to quickly go more in detail to an approximation by linearization. This is something which we will need repeatedly. So what is this all about? So I need some space now. Clean things up. Let's do this. Don't do this here anymore. Essentially, if these equations which I have here would be nice linear equations and didn't have that nasty sine term, I could actually write things as linear algebra, and then when I have linear algebra, I can actually solve for terms in the linear algebra equation. So how are we going to do that? It's very simple. We're going to do an approximation and say, because the nonlinear term is bothering us, and we simply say sine x2 is approximately the same as x2. And this is usually true for x2 roughly in the interval from minus 30 to plus 30 degrees. Okay? That's an approximation. You can try this out. You will see it holds fairly okay. So let's assume our desired or the equilibrium point or whatever is in that particular range, so we can make a very simple linearization. That means we replace x2, sine x2 with x2 everywhere. What does that do to us? Well, it's very nice. We can basically go into this equation up here and get rid of this term. All right? And we can write the system actually now a slight bit different. So this matrix can be written more nicely as minus G over L, but it depends on x2 acceleration. I should make it 0 minus G over L, and here I get a 1, 0, and my state vector is going to be x1 and x2. Okay? So now if you look at this, this is mixed. If I multiply 0 with x1 minus G over L with x2, that gives me the first term. I have to add them together. x1 times 1 plus 0 times x2 gives me this term. So I nicely created actually the same equation. And now I'm completely in notation, which is matrix vector plus another vector, which is a nice algebraic equation I like to work with. Should be emphasized this kind of equation, if we now basically write this as the state equation at the first order differential equations again, and we have basically this other term back here. If we write this just in generic form as on the slide, times 1 over ml squared 0. This is a very generic form, which is usually written as x dot equals ax plus by b. And we write this here, capital X dot, so this is now vector, equals a times x plus b times u. This equation here is a most general linear systems equation. You find this in linear systems analysis all over the place. And it's very easy and very interesting to manipulate. So the moment where you're in such a form, we actually can do nice things. We'll get back to this. We'll see these equations more often again. Now, let's go back to what we want to do. We wanted to find the equilibrium point. So I'm back to this equation up here. And now I basically want to solve things, which is nice. Let me get rid of all of this here. I don't need this anymore. I really want to focus on the equilibrium point again. And my equation, which was not solvable before, we have actually 0 equals minus G over L. It used to be sine, but now it is x2, which is nice, plus Kp x desired minus x2 times 1 over ml squared. Now I can solve for x2. And that basically has already happened here on the slide at the bottom. So we get x2 equals Kp times x desired divided by Kp plus GML. Okay, so this is our equilibrium point. Okay, look at the slide at the bottom down here. So that's your equilibrium point. Good, we did it. But what did we accomplish? So what does it actually mean? And one thing to notice, now going back here to the big equation, that's why I wrote it in very big terms, so I hope you can see this nicely. Our goal was, remember, our goal was that x2 equals x desired. That was the goal of our control. Now, this is not what we got, okay? x2 equals all kinds of stuff, multiplying times x desired. We can make this a little bit clearer, actually taking the x desired as a multiplier out of this fraction. Let's just write x desired, look at it like this. So essentially, x2 equals x desired, but there is a pre-multiplier, which is annoying. So what does this pre-multiplier mean? It's the proportional gain in the numerator, proportional gain in the denominator, and then there is a term which depends on G, M, and L. So what was this? I just put some silly remind me later. I don't want to be reminded later. Go back to my slides. Okay, here we go. So essentially this term, if GML would not exist, we would just have KP divided by KP. That would be nice. That would be 1, and that means x2 equals x desired. So that would be perfect. But that's not the case. So the GML term here is bothering. So what does it mean, GML to be 0? Well, it means a couple of things. If G is 0, that means there's no gravity. Then gravity doesn't bother us, and that's the reason why we would actually reach our position with a PD controller, since there's no gravity term which pulls us down. If M were 0, that this means we have no mass. Well, if without any mass, we don't really have a control system. It's not particularly useful. If L is 0, that means the pendulum actually has no moment arm. Okay, there is also no control system. It would be just a little point mass which we are turning, and the point mass being turned doesn't change at all. So it's a little bit boring. So GML we can usually not manipulate. They are kind of part of our physical world, and they're supposed to be that way. But one thing we can manipulate is KP, so the proportional gain. And you can just play the game now. So what does it take to achieve X desired, at least an approximation? It's very simple. Let's make KP really big. Let's look at my big equations. KP becomes really big, like 10 million. Then you have 10 million here, 10 million there, and then add a tiny little bit, GML, to 10 million. That means 10 million divided by approximately 10 million is 1. That's actually a very important insight. If we make our proportional gains very big, we can overcome any form of error. We basically force the system on the target. And that looks great here in these continuous differential equations, works just fine. As you will see later in the lectures, the moment we take our continuous systems to the discrete time domain, this is not going to work so well anymore. But for the moment, we can just learn that by increasing the proportional gain, we're basically reducing the error of the system from its desired and forcing it to where we want it, which in theory is a good concept, practically not quite feasible. So in the end, you will find out our KP gains cannot become too big, otherwise the system becomes unstable and literally explodes. So at this point, let's do one more thing. Let's insert our integral term. I talked about this for a tiny moment, that it will overcome our gravity problem, and you will see in a second how this works. So I am back to my linearized system here on the slides one more time. Let me just write this over here, and well, yeah, let me just redo this and develop it. It's going to be fairly fast. So we have x1 dot x2 dot equals. Now we have a matrix 0 minus G over L, 1, 0, matrix vector multiplying x1 and x2 plus my motor command tau times a vector 1 over m square 0. Okay. So I wanted to keep those brackets open so I need more. I will now introduce the integral controller equations. The integral controller equation is actually x3. It's a new state which we have generated equals x desired minus x2. So that's a typical integral equation. So we'll talk about this again and again. So we have the change of a state variable x3 depends on the difference, that means the error in position, x desired minus x2. As long as there is an error, x3 will grow, x dot 3 will grow, x3 will grow, that means x dot 3 has a non-zero value. If this becomes 0, then x3 will not change anymore. So x3 becomes a new state which changes over time. And now we can essentially insert x3 in our system of equations. So we need a new state variable. That's very important. So we create some kind of hidden novel state which does not really exist. It's a control state which we need. So we basically create now here x dot 3. Now I can finish my matrices. Here I'm going to get basically 0 minus 1. And I have to squish in a vector of zeros, zeros, and zeros. So boring, but you see it nicely on the slide. And we get a state x3 here. And this here becomes also a 0. Okay? And now we have a new system of equations which we have to solve. The interesting component now here is basically the x3 state. So our controller, I forgot. Our controller is now a PID controller. Here our proportional term is as before. Derivative is as before. And look at the last term, it's k1 times x3. So the u integral equals a integral gain ki, sorry, not 1, ki times x3. This is the new additive term which we're going to get. Now we have to basically insert this controller back into here for tau. So it's the same exercise as we did before. I'm not going to go through this entire exercise, but we can already look at one component. That is, let's look at the bottom equation here. X dot 3 equals what? Equals minus x dot. Okay, so there's a mistake in this slide. These should not be dots. These should be undotted variables. It's not here on my whiteboard. So it's going to be x desired minus x2. And this now has to be 0, remember, in our equilibrium point analysis. And the only way this is 0 is going to be x desired equals x2 is going to be 0. So we already forced the system in state to be on the desired state. What is going to be different is that the equilibrium state for x3 will be a slightly more complicated term. We actually will analyze that term at some point in the future and look at this. But essentially, it depends on the gravity component of the pendulum. All right, and that was essentially the end of the lecture. The idea was to go from the basic foundations of linear control, what our plans look like, our control diagrams look like, going to more details to the first basic linear controllers, in particular negative feedback controllers, looking at system models in a simple equation like the pendulum, and putting a controller in there and seeing what a PD controller and a PID controller in the end can accomplish. All right, thank you. I'll see you the next time. Bye-bye.